Good morning, everybody. Thank you very much for coming, and thank you very much to the organizers for giving me the opportunity to talk at this awesome conference. Actually, speaking of opportunities, I think there is an exciting opportunity that the Haskell community is missing at the moment. I think Haskell would be a really nice language for graphics programming, but we are held back by our legacy tool chain. And, well, who has written Haskell code before? Okay, most of you, not too surprisingly, as everybody was laughing about the monad jokes, I guess. So then you know this, right? This is the prompt of GLCI, the interactive interpreter for the Glasgow Haskell compiler, where you can enter your Haskell expressions and it'll evaluate them. Well, GLCI is a REPL, which is actually quite an old concept introduced with Lisp together with functional programming. But unlike functional programming and looking at Lisp to Haskell, the REPL did not change much, which brings us naturally to the question of, is this all we can do? So you've all written, most of you have written Haskell code. It usually looks like this. So you've got an editor on one side, you've got a terminal with the REPL on the other side, and you switch furiously between them. Depending on the sophistication of your Linux, Windows, Mac OS setups, that's going to be more or less smooth, and maybe you've got an editor plugin and 50 other things configured, but it doesn't change the basic thing. And there are at least 4 big problems with that. So number one, whatever you do in the REPL is not persistent. It's like your editor forgets what you typed yesterday. It's quite annoying. And then a line-based interface, well, to those of you who enjoy historic readings about computing infrastructure, you may know text editors started line-based too, but we moved beyond that. So why not with the REPL? And then manual switching between the editor and the REPL, you always kind of reload your code, re-execute the same things. That's quite inconvenient. But most importantly, for the purposes of this talk, well, you're stuck with text. So what's the alternative? Well, one possible alternative is Haskell playgrounds. So that may look like this in this environment, which Noon already mentioned, Haskell for Mac. You've got a setup which looks somewhat similar on first sight, but on the right-hand side in the playground, you've got a persistent editor window. And all the REPL-like statements you type, they stay there. Whenever you change your program, you change any of that, it's all evaluated automatically and re-evaluated. But most importantly, this allows us to go beyond text. And so let's have a look at how that might look like. So as an example, I'd like to run you through what's called fractal tree structures. That's actually quite a nice structure to explain recursion to people. So we've used it as part of a new Haskell tutorial, which I'll mention again a little later. So what's a fractal tree? Well, it all starts. I can't run with this. That's bad, because I do like to run around while talking. Usually I jump too, but I think then it will just fly. Anyway, this is the baseline. From that baseline, we construct a square. On top of that square, we put a triangle. And then the 2 top sides, what I like to call the roof, of that triangle, that's the baseline for the next set of squares, and so on, and on, and on, and on. So that quite nicely visualizes recursion, recursive structure. So to program this thing in Haskell, well, we need a simple graphics library, right? So let's start with points as a pair of two numbers, and then a line as 2 points with a starting and an end point. And a path is a list of points which we can use to construct polygons with this function, which gives us a picture object which is a path together with some attributes like the line color, fill color, things like that. And then if we have several of these picture objects, we can combine them, superimpose them into a nice picture. Okay? So let's, and there are 2 more helper functions. One is to scale a line, keeping the starting point the same, then extending the line in whatever direction it goes. And a second one to rotate a line, again, around the starting point of that line. So let's use that to write fractal trees. Now, can you read this in the back? Yeah? Awesome. So you don't have to read all this. Don't worry. No. All the interesting things that will happen. So let's start with a polygon, right? So we get a polygon definition here, just a list of points, gives us this polygon with 5 corners. Then if we delete 2 of those points, we end up with a triangle. And then we've got this auxiliary function stump predefined. A stump here is exactly what I showed you before, the square with the triangle on top as a single polygon. So that function returns actually 3 values, the first one being the path of that polygon, and the other 2, which we'll use in a moment, are the 2 new lines for where the recursion is going to happen. So if we draw that in that polygon, then what we get is exactly that initial stump for the tree. So this is one picture element, so we have to put in a list. And this is what we had on the previous diagram, right? So let's take that code, let's take that call to that stump function and put it into what will be the recursive tree construction. Now, we call the stump, we get the path out, we draw the polygon, we end up with the same thing. Now, let's add some recursion. So instead of just one element in this list of picture objects, we want to add the further objects that we get by recursively calling this function. And so we call it on the second argument, which is the right line of this stump. And so we see when we increase the iteration count, this tree is growing. Well, it's not a tree yet. It's at least growing, branching out on one side. But if we replicate that same thing for the left-hand side, so we get a binary recursion, then suddenly it starts to look much more like a tree, right? And then we can just up the recursion count to get something a little bit more interesting. So this is a fractal tree. Well, all right. So let's start to change it around a little bit. So for starters, we can change the color of those polygons. Or if we look at that stump again, it's got a right angle on top. We could change that angle to something a little less symmetric. So then we get a slightly slanted structure, and the tree is no longer symmetric, right? And then going even further, that square, instead of using a square, we could use a rectangular structure. And so where the stump is higher than it is wide, that will give us a more natural-looking sort of tree. So we just scale these 2 lines on the side, and then the overall tree structure looks quite a bit more interesting than the original very symmetric structure. Okay, so that was just a brief exploration of this idea of fractal trees. Now, all these properties we changed, the color, the various ratios and angles, we still had them be the same for all the recursive calls. Now, if we really want nice fractal trees, we ought to make them, these properties depend on the recursion depth. So if we do that, then we can get some really nice pictures like those. So they're quite filigrane structures depending on what properties you choose. So as I mentioned before, this is actually part of a new Haskell tutorial that Gabriele Keller and I am writing at the moment. There are something like, I forgot, 8 chapters, 9, something like that at the moment. And 3 of them use those fractal trees as a running example. I think it's quite a nice structure. So if you're interested in that, or if you know anybody who wants to learn Haskell, well, send them there. All right, so we made some pretty pictures, but they're all still pictures, right? Can't we do better? Can we add some animation? That'd be more interesting, right? So to add animation, we need a slightly richer graphics library. So we'll stick with polygons for the moment, and we've got a new function, shape node with path, which given a path returns a node, which is our new substitute for the picture object in the previous setup. And these nodes, they come with a few interesting attributes. In particular, there are action directives, which are actions for animations. I'll show you 2 examples in a moment. And even more excitingly, optionally, such a node can have physical properties, which will be the basis for simulation by a physics engine. And then those nodes themselves, they can have children. Okay, so we are moving to a tree structure. So as for the animation directives, we can translate a shape along a vector, for example, or rotate it by a rotation directive. And with physical properties, we can give things mass, and then they go by whatever gravity dictates. Now, as a last point before we get into code, given this structure, what we did in the previous implementation, we created a list like this of picture objects at absolute positions, which has made up this tree structure. But that tree structure wasn't available in the graphical representation anymore. Once you move to animations, you actually want to preserve that hierarchical structure. And that's where this node children property of those nodes comes in. Okay? So let's do this. So similar setup, we have stump predefined. And this time around, this is our scene description. So any in this graphics library, every animation happens in a scene. So in that scene, we call this function fractal node, which is going to be the replacement for what the fractal tree function was in the previous example. So again, we are giving the non-recursive version, setting some properties already, and that gives us our familiar tree stump. So now, instead of constructing this list of elements, we add to the children of this node, and as you can see, the result value of this function is a maybe type, because this time we can't return an empty list, which is what we did for the base case in the previous setup. So we have to go through maybe. And then let's just start with one of the recursive calls. Going by the same idea, so we get the 2 left and right roofs from that stump call. And then if we add the second recursive call, we end up with the same structure that we had in the previous example. But now we've got the opportunity to add some animation. So just as an example, let's take this animation which runs an animation sequence forever, meaning in a repeating loop. And that sequence has two parts. There's a rotation, and then there's a rotation which is reversed. So it's just the opposite of the previous one. And that goes on and on and on and on. And just by adding this animation directive during the construction of this node to the node, we'll get a nice effect of kind of a wiggly tree. Okay? So that wasn't much work for some additional action, but that's not all. So the next thing here is, and don't worry, we don't go through all this code here. I mean, it's not that much more code, but what's happening here now is that instead of during the construction of this tree, creating the tree at once, we use animation actions to create the children with a delay. So then when the tree comes up and they fade in, and then we add gravity. Okay? So that's more fun than just a static picture. Come on. All right. So all this is based on an animation and game programming framework called SpriteKit, which is a part of Apple's ecosystem. So macOS and iOS, watchOS and tvOS, whatever. So let's generally, what I said in the beginning is that we are missing opportunity here, that our tools are holding us back from doing graphics programming. But there's a second ingredient which is typically missing. And that's a graphics library, a good framework. There typically, you have two extremes. You can have a high-end, state-of-the-art, industrial strength. This is what your iOS game, iPhone, Android games are written with type of library. Looks great, awesome, but the API, very stateful. You've got an object graph, you mutate all over the place, race conditions back and forth, quite awful. Actually, SpriteKit isn't that bad, but still. This is the Objective-C version. You don't want to write that, right? Or you take a native Haskell framework, which has nice and pure code, but on the graphics side, it's slightly lacking. So which one do you pick? Well, maybe we can have a compromise. There's really no way we are going to bootstrap a state-of-the-art animation framework. Not because it's impossible, but because it's a lot of work. So maybe we can take one, like SpriteKit, and put like a functional, some icing on top of it, like syntactic sugar just for API. Right? And then the idea would be that the representation of the structures that we are working with, they're just algebraic data types, nice, immutable Haskell structures. And then there's some magic, oh, I was too fast here. There's some magic going on under the hood where whenever we transform those pure data structures, these changes are automatically transcribed into the mutable object graph. It's not our code that's doing that. It's somebody else's code. We don't have to touch that. It's going to be messy code. So that's a standard setup for SpriteKit. So you start with the scene, as we did with that second version of the Fractal Trees. And then underneath the scene object, we can have nodes, and they can have children as well. So it's this tree structure we've seen before. And then on this tree structure, on the mutable API, this is what you write in Objective-C, you can do all kinds of great effects. There's a wide range of things you can do. And how does the code look like? Well, there are lots of callbacks. In particular, one, the master one, I would say, is this update method on the scene object. And that just, well, it just gets a time, and that's it. So what does it do? well, whatever it likes. It just mutates all over the place. It's called object-oriented programming. So in particular, it might edit the object graph or change some properties of those objects, right? So we could do that in Haskell, right? We could just rack everything into the I/O monad and write the same messy code as in every other programming language. So when I say Haskell here, imagine ML or whatever your poison is, right? I'm just sticking with one thing, but I don't try to be exclusive. We are inclusive here, as we've said before. So in Haskell, what we want to do, we want a proper function. Okay? So our scene description is just a record, a Haskell record. And then we've got a function scene update of type scene update, which takes a scene to a new one. So the way that works is that the library takes a representation of a scene, including everything hanging down of it, below it, and it lazily marches that over into one of these Haskell representations. Then we call a vanilla, pure, nice function, not even in the I/O monad, just a pure function, and we get a new scene representation. And then the magic happens. Behind the scenes, there's a diff computed of whatever changes happened, and those changes are automatically applied to the object graphs. And we get the same behavior as we would if we would write that corresponding Objective-C code. Only we wrote Haskell this time around. Okay? Does that sound like a plan? So now SpriteKit is a game programming framework. So let's write a game. So one of the golden rules of speaking at conferences is do not do any live programming. I'm going to break this rule now. But don't worry, if everything goes really wrong, I've got a screencast as a backup. Okay, so let's see whether that works. Okay, it's empty at the moment. So this game will be familiar to you. But let's just start with, so here we already go in that okay, so this is my scene definition. I can put this into the playground, and we get a scene. It's not very interesting yet. It's quite black. And so you should be, I didn't ask. You can still see that in the back. That font is actually bigger than before, right? So let's add something interesting. We need a hero, like every game needs a hero. So let's get a hero. So we've got some textures here, and as I promised, those will look somewhat familiar. So let's get the first one in. Do you recognize this guy? Okay, so we've got a hero. Let's put it to work. So we define a node. This time we don't use a shape as our base for a node, but we use this texture. And this thing got a name, and we put it in a particular place. And so we just add this to the scene. And the scene children are list, and we just put the bird in here. Its name is Lambda. And here it is. So, okay, that's nice. It's still boring. So we've got, as you might have seen, we've got a few more textures to play with. In fact, we have got 3 different ones with different wing positions. So let's add an animation cycling through these textures. So that's actually quite easy. So we add one of these node action directives, which we've seen before. And this time, the action again runs forever, as we had with this wiggling tree. But it is going to be a flapping action. And we'll add this down here in a where clause. And now if we look at the bird again, it's flapping. Okay, that's our first animation. But it's dark. Which bird wants to fly in the darkness? So we better get some background going here. So a nice sky color, that looks about right. And but this bird, it looks quite heavy, doesn't it? So we better add some physics here. So that's just a physics body as we had before with the tree. And we also define the overall physics for the scene in the scene definition. So that just specifies the gravity, and lo and behold, the bird is too heavy, which is quite sad. So we want to help it. So we want to press keys for the bird to kind of fly, right? I try not to jump too much because you saw what happened before. And so to do that, we add an event handler. This is like the update function. It's another callback. And here, actually, let me give a bit more room. Oh, okay. So that update handler has to go into the scene. So we've got a scene event handler, and that's the function we just defined. So that gives us key presses. So let me show you down here. So whenever we press a key, what we do, we change the game state. A Boolean called key pressed is being set to true. So to make use of that Boolean, we introduce this update function of the form. That's the update function from the previous slide when I explained the scene kit setup. And this update function, whenever a key is pressed, calls this bump lambda, bump it up. So we want to add an action dynamically. When a key is pressed, we add an action to the tree, not like before where we added the actions when we constructed the thing. We do that dynamically now. And so bump lambda is calling action which are predefined in different file. And now I should be able, I forgot one more thing. I have to actually set the update function here in the scene as well. And so that's in here. And now, whenever I press the key, the bird kind of flies. That's nice. That's quite a simple animation. You would expect the bird to tilt a little when it flies up, right? So down here in the update function, when we don't have any bumping to do, we could add another action which I call tilt lambda, which adjusts the position of the bird, the rotation. So we use that here. And with that, it looks a lot more realistic. Okay, so now we can have nice dives. Okay, so that's our hero. But the scenery is still quite boring. So we need some more textures. Luckily, we've got some more to play with. In particular, we have a ground texture, which looks like this. Now, this is a side-scrolling game. So how about this scrolling? How can we realize this? This should go to Keynote. So, well, the way we do this is this setup. So we add this texture more than once to give us the ground, and then we attach a movement action. And once the first tile, the leftmost tiles, leaves the screen, well, we put it back. And then we move again. And that way we get an infinite, are you okay? We get an infinite side-scrolling game. So let's have a look at how that looks like in code. So let's just look at the ground by itself by wrapping it into a node. And these sprites already come with the actions attached. So you see they move, and once it's scrolled far enough, it jumps over to the left. So that looks good. So we'll have a few moving nodes. So we'll actually make a parent node with all of them. And that gets a name too, moving, which we'll use later on. And we've got the ground sprites in here, but those moving nodes, you have to make them part of the scene together with the bird. Okay? And so once we've done that, we can still fly above the ground, but the ground is moving. So that's nicer. But still, we need a little bit more scenery. And luckily, we've also got some sprites for a sky line, and that moves slower to give a little bit of a kind of perspective-like effect. So what we are going to do here, this is a list of sprites. And we are going to add the sky here. And now it looks a lot nicer, right? But the ground is kind of not very solid so far. So let's see what we can do about this. Hello, Keynote. So that's the setup so far. Now, the bird is already a physics object, right? And we could make the entire ground. We could have Earth as an object, but that's a bit silly because we really want to know only one line. We want to know, does the bird touch that line? And if once it does, we want a collision, we want to call back to a contact handler, and we want some physics like bouncing off happening. So that's the plan, okay? Let's see on how we can realize that. So first of all, we add another node for the ground physics. And that introduces this edge-based physics body, which is just an edge and not an entire volume. So ground physics, it's also a node, as you can see from its type. And so we want to add that to the scene as well. And now, in order to define which objects interact with which other objects, the physics body of the bird needs a little bit of help. And it needs some categories. The basic idea is in SpriteKit that you can give different categories to different bodies to define which one collides with what and when to call a contact handler and when that's not necessary. So that's what we did. And now, when the bird drops down, it bounces off the ground. So that's good. Got some physics going here. But we want to note that contact because it's game over. All right. So that's another callback. So what we've got up here, together with the other callbacks, we have a, no, it's not here, sorry. In the scene world definition, we've got a world contact, world contact it begin handler. And it's calling a function contact, which we are going to define down here. And that contact function, the main thing is happening here when the contact gets the two objects which are in contact, and we check if it's the world the bird is contacting with, then our game state changes to a crashing state. And that crashing state we can now notice in the update function, which updates the scene once per frame. So we introduce a new case here. And then once that happens, once we have a crash, the game state goes to game over, and in that state, we don't do anything anymore. But we need a crash handler. We want something to happen on the crash. The bird should roll, and then the animation should stop. So we'll have another action for that, which is being called here. And so let's see what happens now. So once we crash, the bird rolls, and that's it. Okay? So that's nice. Now we can fly around, and it's easy to stay off the ground. So we want a bit more of a challenge. And so as you know this game already, it won't be a surprise. We want some pipes. So there's a downward pipe, and then there's an upward pipe, which looks like this. And we want to generate these pipes at regular intervals and at different heights, so we have to fly through them. And again, we can do this with actions. An action with a delay every 1.5 seconds, it spawns a pipe. So we do that by adding, as always, another node to our scene. So this time around, it's the pipes function. And those pipes nodes, they come with a custom action to spawn a pipe pair. And there's some random number generation going on. The details are quite boring, but those pipes, those we have to add to the moving nodes. We don't put them into the scene, but they're part of the stuff which moves around. So once we've done that, lo and behold, there are pipes. And they already come with a physics object attached. So if I crash on a pipe, that's it, like with crashing into the ground. So now we are getting there. We have to work to survive. But, well, just surviving, that's not good enough, right? We want to see who's best. I mean, it's a game after all. So we need some sort of score here. And so we'll introduce yet another, the last one, node, a score node, which is just a number, which we add to the set of nodes in our scene. And you'll see the effect. So we've got the 0 here, and nothing happens. So that's quite disappointing. We want a reward one way or another. And I will get back to Keynote. I don't know why it doesn't want to go back to Keynote. So this setup, the bird already got a physics body. So one easy way to solve that scoring is to introduce another invisible physics body as a sentinel for when we just pass the set of pipes. And that has to move with the pipe, so it's accurate, right? So actually this, what's called the contact physics body, is already part of the pipe pair setup, but we need to extend the contact handler to deal with it. So let's extend our contact handler, which is down here. So we replace it by one which has one more case. In case we contact a score body as opposed to a world body, which is pipes and ground, then we want something else to happen. We set this game state variable bump score to true. And whenever we do that, in our update handler up here, we have a new case, bump score case. So in this case, when we get into this bump score situation, then we call a function called, which is again setting up an action called inc score for incrementing a score. So inc score just takes the current score, which is part of the game state, adds 1, and then runs a custom action on the score on this node, same name, to set the new label. So let's try this for the full experience, and yay. Okay, so now we can have one of the prizes for whoever gets the high score. I just made this up. Again, we feel to get back to Keynote. So that's it, right? So we just built a game in Haskell. Now, this Haskell wrapper of the SpriteKit framework was so far only part of the Haskell for Mac environment. But today, I'm going to flip the switch on the GitHub repository to make it open source. And the build system is still not really up to scratch. I mean, it's tied to Haskell for Mac, but we can change that. And so if you're interested, have a look at it. As I said, all the magic happens behind the scenes, that kind of applying the diffs to the actual object graph. If you look at that, you may lose your faith in functional programming. So just stick with the user level API. Thank you very much.
Thanks. That was amazing. So we've got time for a few questions. So if you just raise your hand, we'll come out to you. So any questions? Yes, there's one here. I'll just wait for the microphone.
This is incredibly cool, right? And you can obviously see the applications for where you're writing something in Haskell that brings Haskell to animation. Do you think there's an opportunity to bring animation to Haskell? Like, I do a lot of work with web servers and databases. Do you think that kind of live visualization can help?
Yeah, so I very much think so. That's actually what I've been thinking about the last few months. I think what we've got here is an incredibly opportunity to make learning programming simpler. So we use this in a very primitive form in this tutorial, which I mentioned, where we use things like these fractal trees to explain recursion, where when we introduce expression trees and binary trees, we have visualizations of them. So in the tutorial, when you run through it, you see the trees you're constructing. You don't only just get the ASCII gunk of a show instance, but you actually get a two-dimensional representation of a tree. And I think this is the tip of the iceberg. I mean, there are much more well-known people than me speculating about this. So anybody who has not yet looked at Brad Victor's work, go to veridream.com, have a look at it, and then you'll see that I think our current programming tools are quite too simple, and I think we can do a lot better. It's not trivial, but especially in the scope of functional programming, I think this works very well because most of the code we are writing is functional. So the entire effect is given by the mapping from input arguments to outputs. That makes visualization a lot easier than in an imperative state-driven update scenario. Yeah, so I think there's a lot of potential there. Thanks.
Cool. Any other questions? Oh, awesome. All right, well, we're going to take a short break now, so there should be, with any luck, some morning tea outside, and we'll come back here at 10:30. So let's thank Manuel again for an amazing